Okay, let's look at this gas law question from November 2017, question 5. Here are my things from the data sheet, the formulas and all the values from the data sheet. And remember now, I can't write these nice fractions, so you'll just have to improvise these. Okay, where the balloons are sent into space to gather data. The balloons usually burst at a pressure of 27,640 pascals and a volume of 36,3 cubic meters. The data collector then falls back to Earth. The gas in a certain weather balloon has an initial volume of 12,6 cubic meters and a pressure of 105,000 pascals at a temperature of 25 degrees C when it's released into space. Calculate the temperature of the gas in degrees C in the balloon when it bursts. Okay, so let's have a look at this question here. In this question here, you can see a pressure and a volume, and another volume, and another pressure, and a temperature, okay? And they're asking you to compare when the balloon leaves the ground to when it gets into space. So obviously as the balloon gets into space, the pressure in space is less. That's why the balloon is going to pop up in space. Also remember, it gets cold up in space, so you can probably assume that the temperature is going to get colder. The next thing to look at now is the units. This is in pascals, this is in cubic meters, this is in cubic meters, this is in pascals. That's all good. All our units are comparable and they look like the proper units for gas law calculations, except for this. This temperature is in degrees C, and remember in the gas laws everything must be in Kelvin. So the first thing we're going to do is convert this, okay? So we know that it's degrees C, Kelvin is degrees C plus the standard temperature of 273. So T equals 273 plus 25, which equals 298 Kelvin. Okay, so that's the first thing. So let's look. We know this is going to be T1, okay, because this is the temperature on the Earth. We're going to use P1 V1 over T1 equals P2 V2 over T2. We're going to use this because that's what we're doing. We're comparing the temperatures and pressures of the balloon in two different situations as it goes into space. So we're going to call T1 where it's filled on the ground. So then V1 is going to be 12,6 and P1 is going to be 105,000. Okay, so then let's make this balloon picture smaller. Then we can have a look here. We need to find T2. We don't know what's T2. Do you agree? So then do we know V2? We know V2. They tell you it pops at a volume of 36.3 cubic meters, and the pressure that it pops at, which is P2, is going to be 27,640. Okay, so we're fine using P1 V1 over T1 equals P2 V2 over T2 because all of our units are the same and we've converted the temperature to Kelvin. So we can start here with this. So I'm going to write it as a division sum, P1 V1 over T1, okay, equals P2 V2 over T2, and let's put the figures in here. So P1 105,000, and then my V1 is 12.6, and this is going to equal P2 27640, V2 36.3, and T2 we don't know, divided by T2. Okay, what have I forgotten here? I have completely forgotten to type in over here divided by T1, which is a bit silly. Okay, divided by 298. That's the temperature in Kelvin. Okay, so now we will do the wonders of algebra, and you will put this on your calculator. Hopefully you've got this on your calculator already set up on the fraction thing. But this is going to work out if you put it in your calculator. Let me just quickly do it in my calculator. I get a rather large number, which means I've done something wrong. Let me try it again. Okay, let me have a look here. I think it's supposed to be something like 225,996. Okay, and this is going to be in Kelvin. So 225,996 is going to work out as 226 Kelvin. But the question didn't ask me for the temperature in Kelvin. Look here, it asks you for the temperature in degrees C. So the temperature in degrees C is going to be 226 minus 273, which gives you negative 47 degrees C, and that will be your final answer. Okay, now it says to you, calculate the initial amount of gas in moles in the balloon. So we know at STP, this is the molar gas volume, but the gas laws taught us this formula, PV equals nRT, where pressure times volume equals the number of moles times the molar gas constant, and then the temperature in Kelvin. So we're going to use PV equals nRT because this is the only formula we've got that directly is going to give you moles. Okay, so here PV equals nRT. The P here, our units are correct as well for this formula. We're in pascals, okay, and we converted the thing and the volumes in cubic meters, and we converted the what do you call that thing, the temperature in degrees C to Kelvin. And what am I missing from this formula? The temperature in Kelvin, 298. So this is what happens when you set up your equation. PV equals nRT. This is the pressure, this is the volume, this is before it leaves Earth, equals 8,31 times the temperature in Kelvin. So if you do this in your calculator, let me see if I can do this one correctly. I suspect I have done something wrong. Goodness, me and this calculator. I certainly hope you have your calculator at home with you. There we go, that looks better. I've got something like N equals 534,25 moles. That really looks like a lot of gas, but it's not a surprise, because have you looked at the volume of this? I mean, there's like 1,000 cubic decimeters in a cubic meter, so really this is a massive amount of gas. So it's not a surprise that there's a lot of moles. And that should be your final answer.